Greetings and welcome, friends. Mr. Waddy here. I'm taking a look at section 6.2 called Bisectors of Triangles. We're going to today look specifically at right perpendicular and angle bisectors of triangles and discover some interesting features of those special segments or lines or rays, okay? And one of those features is that they will have a common point, all right? So check this out. When three or more lines, rays, or segments intersect in the same point, they are called concurrent lines, rays, or segments. Now, notice they say three or more because it's 2 points, two lines intersecting. Just happens all the time, so it's not very interesting. It doesn't really need a special word for it. But concurrent is interesting, okay, when there's three or more. The point of intersection of the lines, rays, or segments is called the point of concurrency. So here in this picture, you could see that there's a point of concurrency. In a triangle, the three perpendicular bisectors are concurrent. What does perpendicular bisector mean? That means that when let me switch to my classic yellow, that DP here is a perpendicular bisector. That means it bisects segment AB into two congruent parts, that D would be the midpoint, and that it's perpendicular to that. And if I was to draw all of the perpendicular bisectors, that they would actually share a common point. And it says the point of concurrency is the circumcenter. Now get your giggles out now, friends, all right? I understand. You'll see why this is interesting in just a moment. It says circumcenter theorem. The circumcenter of a triangle is equidistant from the vertices of the triangle. So if I've drawn all of these, right, perpendicular bisectors, it turns out that these blue segments are equidistant. Those are the same distance. Now, the word circumcenter, right, has kind of a prefix for circle in there, and the word center. Now, how is this going to relate to circles? Well, let me show you here. Let me show you here. Open up some geometer sketchpad. So I've got a plain triangle here, right? Any old triangle you can see. Okay. So let me select these sides and go to construct midpoints. Voila. Let me select a midpoint in its side and go to construct perpendicular line. So now that line is a perpendicular bisector. Let me actually even select its color. I like the old orange right there. And let's construct the perpendicular bisectors for the other two sides of the triangle. Voila. And notice that wherever I go, that's so crazy. Those lines are concurrent, right? I don't think I would have seen that coming. And even for like an obtuse triangle, that point is outside the triangle, right? But those lines are always intersecting. Now, Geometer Sketchpad won't let me snap to more than one line at a time, but I assure you, those are the same, okay? And we just saw, they claimed that if I connect that point to my vertices, let's see, let me change colors again, and I'll make this a dashed line. Their claim is that these distances are the same. Okay, let's see if that's the case. So I'll select those three. One at a time, one at a time. Display measure. Here we are, lengths. Well, what do you know? And no matter where I draw that, notice these lengths, they're always the same. Whoa, that's pretty crazy right there. Right, so I can have all sorts of triangles, but those lengths are always the same. Now, how does that relate to circles? I don't think we've officially defined it yet. Maybe in passing I've mentioned it, that a circle is the set of all points equidistant, that distance being the radius, from the center on a given plane, okay? Now, I've just claimed that points A, B, and C are now equidistant from C, and that means that A, B, and C would lie on a circle. Right? If they're all equidistant from this point, that means they would lie on a circle. at center C and radius AD or CD or BD right there. So let me draw this circle and notice what happens. Wow. I'm assuming you guys are like, wow, right? Just shocked right now. I know it's crazy. I know it's crazy. Whoa, now that was crazy. Let me get my selection tool here. And so now wherever I draw this, that point is helpful for me because this concurrent.
Will Ryan, if you're in the building, please report to the front office. Will Ryan, please report to the front office.
This point of concurrency will be equidistant from my 3 points. We'll see how we can put that to work in just a moment. And it's called the circumcenter because it's the center of the circle that circumscribes the triangle. It's the circle that hits all 3 vertices of the triangle, and that will always be the center of that triangle. Wow, pretty amazing. I think so too. So let's see. Let's do an example. How is this helpful to us? Well, I'll show you, my friends. I'll show you. Here we go. Example 1. You guys can follow along. You've got the stuff. Example 1. All right, solving a real-life problem. And this is how you would solve it. It says 3 snack carts sell frozen yogurt from points A, B, and C outside the city. Each of the 3 carts is the same distance from the frozen yogurt distributor. Find the location of the distributor. Now, this I realize is imagining that these would all be that this frozen yogurt distributor can conveniently just drive off-road. And that would not necessarily be a valuable thing for him to do, right? Just like plow through buildings as he delivers frozen yogurt. That's somewhat disrespectful, I think. So let me get my compass tool here, see if I can get this to be a 90. Oh, there it goes. So watch, I'll also simultaneously show you how to construct perpendicular bisectors from a sketch. So maybe take a moment, go grab a compass. Pause the video if you need to, right? And grab a compass. So watch this. So to construct a perpendicular bisector, I can actually swing and same radius, right? Swing right there. And my perpendicular bisector is going to be the line that passes through those 2 points. So let's draw that perpendicular bisector. All right, so let's see. Yeah, I'll draw this in a different color. All right, so this is the perpendicular bisector of specifically the segment AB. Let's see, let's get my compass tool again. So from point A, let's see if I got to make it at least past the midpoint for AC. If I'm going to draw this correctly, I'll swipe right wide enough that I can hit both intersections of that circle and swipe like so. Uh-oh. Guys, that didn't work. Did it not work? Why didn't it work? Perpendicular bisector, that should be, wait a minute. Did I hit that right? A, yeah. Oh, okay. I'm crazy. What I was, for some reason, my brain was expecting that they were all going to hit this point. But my compass dimensions, my radius, were somewhat arbitrary. I'm not expecting them to hit that point. I'm expecting my red lines to pass through a common point. All right. Wow, were you guys scared? I was scared. You were scared. Like, I was worried I broke math. All right, I'm constructing perpendicular bisectors here, and I was terrified. All right, so now, theoretically, without even drawing the other perpendicular bisector, I've already found the circumcenter. But let's just construct it anyway, all right? So let me line it up. Let's see, make this a little smaller, at least past the midpoint of BC. And let me swipe it around here. Ooh, actually, let me make it a little larger. It's a little too close to the other one there. All right, I've got a lot of overlaps. Maybe I should have done these in different colors, but that's fine. And like so, bada bing, bada, come on, bada bada. There we go. Right, so connect the intersections of those arcs. All right, so right here, this point is where all of the frozen yogurt should come from. All right, this point of concurrency will be equidistant from A, B, and C. Actually, let me just show that to you, prove it. I could show it visually to you. Wow, that would be such an elegant way to do it. Watch this. Now, if I line this up right and I increase this circle, I should be able to have a circle. That's right, that hits all 3 points at the same time. If that doesn't prove it for you, like that's just like, wow, I love that. That is lovely. Wow. And now when he delivers frozen yogurt, he's just got to like plow through the city. He does not obey the law. He doesn't drive on the road. He's an off-road frozen yogurt deliverer. Just like you, right? Just like you would. Wonderful. Okay, let's keep going on here. So, now you might have noticed some of this when I was in Geometer Sketchpad, but it says, okay, so the circumcenter P is equidistant from the three vertices, so P is the center of the circle that passes through all 3 sides, as shown below. The location P depends on the type of the triangle. So for an acute triangle, P is in the interior, in the inside of the triangle when it's acute, okay? For a right triangle, I didn't show you that. I didn't pause there long enough. I didn't want you to spot it. For a right triangle, P is on the hypotenuse. Wow, maybe we'll do some work with that later. And in an obtuse triangle, P is outside the triangle. Let me go back to Sketchpad just to show you that. So let's see, D is my circumcenter. When it lands on that, actually, wait a minute, guys. That looks as though when it's a right triangle, it looks like it is the midpoint of the hypotenuse. All right, when it's an acute triangle, it's on the inside. When it's an obtuse triangle, all right, there's an obtuse at angle B, there's an obtuse at angle C, there's an obtuse at angle A. Notice that the circumcenter will be on the outside of the triangle. Cool. Good. All right, let's keep going. Here's an example. Ooh, on a coordinate plane at that. Let's see, I might have accidentally given you guys the solution again, who knows? But you can follow along, my friends. Let's see. All right. Oh, no. We didn't. We're good, I think. Maybe not. It says, find the coordinates of the circumcenter of triangle ABC with the given vertices. All right, so step 1, graph triangle ABC. Done. All right, you guys know how to plot points. Here's our y-axis, by the way. There's our x-axis. So 0, 3 is up 3, right? 0, negative 1 is down 1 from the origin, and 6, negative 1 would have been over 6, down 1. Plot those points, draw your triangle. And it says find the coordinates of the circumcenter. Here it looks as though we're doing it graphically, although we could have found the midpoint. Let's do that actually. What is the midpoint formula? Do you remember? Midpoint formula is the average of the x's and the average of the y's, all right, for any 2 points. So let's find the midpoint of A to B here, okay? So the midpoint for AB, so AB, MP, maybe I'll call that, I don't know, for notation's sake, is going to be the average of the x's, so that's 0 plus 0 divided by 2. I can do that in my head. The average of the y's, 3 plus negative 1 divided by 2. I can do that too. What? So AB midpoint is 0, and 3 plus negative 1 is 2. 2 divided by 2 is 1. And notice right here is the point 0, 1. Got 'em. Let's find the midpoint of BC. So BC, midpoint, would have been 0 plus 6 divided by 2. -1 plus -1 divided by 2. Well, the average of two negative ones is going to be -1. It's got to be, right? And so let's see. 0 plus 6 is 6. Divided by 2 is 3. And -1 plus -1 is negative. 2 divided by 2 is -1. I told you it was going to be -1. Over 3, down 1. There we go. And so in this case, those were horizontal and vertical lines. So these equations are relatively easy to construct. They would have been perpendicular to that. A vertical line that passes through this point would be of the form x equals a number, and it would be x equals the x coordinate of that. A horizontal line that passes through this point is of the form y equals a number, and it will equal the y coordinate. And so that's what we see for both of those. This one has no slope, and this one has 0 slope. You could have thought of this one as y equals 0x plus 1 if you really wanted to. And if I wanted, now I could actually find the intersection of those two, which in this case, it's not that interesting because they were horizontal and vertical, is going to be the point 3, 1, 3, positive 1, not the 3, negative 1. So I would find the intersection of those 2 points. Now, if I didn't conveniently have these horizontal and verticals, you guys could check out, I think it was example 5 from the last video about how to find a perpendicular bisector's equation, and you would do that twice. Yeah, their slopes are opposite reciprocals, remember that thing? Find both of those equations, and then I would use substitution or elimination to solve the system of equations and find that point, right? So 3, 1 is the solution. This one, we could kind of do it graphically. But there we go. All right, let's yeah, it looks like they're only ever going to give you the other kind. Let's pick up the pace here. In center. All right. Yeah, we're going to have enough space for this. This is good. We're doing okay. Right. This by the way, this section, these next couple sections are very vocabulary intensive. It's easy to mix up the names of these things, so let's pay attention. Just as a triangle has 3 perpendicular bisectors, it also has 3 angle bisectors. The angle bisectors are also concurrent. No way. What? This point of concurrency is the incenter of the triangle. For any triangle, the incenter always lies inside the triangle. Wow, guys, that's crazy. Let's take a look at what happens here. All right, let me go back to Geometer's Sketchpad. Here, it's my arbitrary triangle. Woo, woo, woo. All right, let's construct some angle bisectors. To do that, I select the point and the 3 sides, and I say construct angle bisector. How easy is that? Let's change its color to orange. La, 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 la. And wherever that angle is that's dividing it into 2 equal parts. Let's see, let's do the same thing over here. Angle bisector. Oh, they intersect. And construct. Is it going to be the same point? Bam! Same point. Did you see that coming? Well, they told you. And so there's that point. And notice no matter where I move this triangle, that point is always on the inside of the triangle, except when it's not a triangle. But yeah, there we go. All right. What else did they tell us? So there's a theorem called the incenter theorem. And what does the incenter theorem say? It's got the word center in it again. The incenter of the triangle is equidistant from the sides of the triangle. Sides. Okay. All right. So how do I measure distance to the side? I wouldn't measure along this orange line, just so you're aware. You remember that? How do I measure the distance to a side? Because look, this along this orange line is not the shortest distance. The shortest distance would be perpendicular to that. So let me construct some perpendicular bisectors. Let me actually change line color here. Oh dear. Oh dear. Oh darn. Darn, 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 darn. All right. I messed up, friends. Okay. All right. Let me get these colors fixed. All right. There we go. Okay. All right. I'll construct the perpendicular bisector, then I'll change its color. So construct perpendicular line. There we go. Change this color to green, something like, and tell you what, we'll even make it dashed. Little dash of perpendicular bisectors. Bam! Just like that. And now let's construct the others. Perpendicular line. Ooh, yes, lovely. And construct perpendicular line. And notice that those are, ooh, you're gonna love the way, look at the way those dashes move as I move it. It's crazy. They're like scrolling around. So notice that it's unlikely, oh, I can get those orange ones to be the same as that, but those distances are different than that. So let me plot some points, and let's figure out those distances. So let's see, let's make some segments. They're claiming that these, oh, that is not at all what it, is that point even real? Oh, it's a fake point. Let me undo. There we go. All right. Let me just do this. I'll construct from there to there. It's going to actually change the, usually it changes the dashiness of the line when I do that. There to there, and from there to there. Okay. Tell you what, I'm going to hide that. I'm selecting it and hitting Control H. You can also hide things by selecting and going to Display Hide. Let's find those distances. Measure lengths. You don't say. Those are all the same. Guys, they're the same. They're the same distance. Okay, that's pretty cool. Now, wait a minute. 3 points that are the same distance from another point, that means those 3 points lie on a circle with center at that point. What's going to happen here, friends? Is the center going to be at E and it's going to have radii E, D, E, F, or E, G? Wow, guys, isn't that's beautiful? Look at that. Wow, wherever I move it, wow, that circle is perfectly inscribed. Inscribed is the word inside the triangle. And point E is referred to as the incenter. Yeah, wow, that's so beautiful. Look at it. Did you see that coming? No way. Wow. Just appreciate its beauty, right? So the incenter theorem. Let's see, I think I've got that copied. Yeah, right? The incenter of a triangle is equidistant from the sides of the triangle. Incenter is made from what? The angle bisectors form the incenter. And then it says if AP, BP, and CP are angle bisectors, then PD equals PE equals PF. So cool. So cool. All right, so let's put that to use. I'm just appreciating the beauty of this geometry so much right now. Now, in terms of like application, these problems are going to be pretty easy ones again. It's just a matter of knowing who's congruent to what. So here we go. It says in the figure shown, ND is equal to 5x minus 1. Let's see, ND, okay, so 5x minus 1. And NE is equal to 2x plus 11. Now, I'm expecting these are going to be congruent. Why? Because BN is an angle bisector, CN is an angle bisector, AN is an angle bisector. They're all concurrent at point N, and therefore point N is going to be equidistant to the 3 sides of the triangle. Wow, look at that. Amazing. So those two, by def of Kong, if the segments are congruent, then their measures are equal. If their measures are equal, let's see, what is NF? Find NF. Huh. Well, ND and NE are equal, so let's say 2x, let's start with the other one. 5x minus 1 equals 2x plus 11. And we'll solve, subtract 2x from both sides. And I will get 3x minus 1 equals 11. Add 1 to both sides, and 1. Oh, isn't that so nice? It's not going to have fractions. 3x equals 12, divide by 3. Were these x's? Yeah, okay. For some reason I thought an n was in there, but that was just the name of the point. And so I'm going to have x equals 4. So x equals 4. They said find NF. Find NF. Well, oh, NF is going to be the same as those guys. Those guys are not 4 units long. They are these units long. So let's find out what ND is. ND is going to be 5 times 4 minus 1. So that's 20 minus 1, which is 19. And if ND is 19, then by transitive property in def of Kong, NF is also going to equal 19. Beautiful, beautiful. I love it. Then it asks the question, can NG be equal to 18? NG be equal to 18. Ooh, wow, explain your reasoning. Now, that segment, this one is 18 right here. Or sorry, 19. And this is the shortest distance to a side. This, NG, is going to be a longer distance because it is not perpendicular. And so it's got to be bigger than 19. So NG is greater than 19, and therefore NG cannot equal 18. Aha, all right. So it's not 18 because it's got to be bigger than 19. That was the shortest distance. The edge is going to be measured perpendicular to that. Let's see, do we have one last example? Yeah, I think I'm going to just do this last example for. Let's see. Thanks for hanging out, guys. And here we go. All right, solving another real-life problem. A city wants to place a lamppost in the boulevard shown so that the lamppost is the same distance from all 3 streets. Should the location of the lamppost be at the circumcenter or the in-center of the triangular boulevard? Okay, well, I think that if it was at the circumcenter, that would be the circle that passes through all 3 of those points. Let me just even show you what that would look like, which would be something like this, and that's an obtuse triangle. So the circumcenter is going to be on the outside, right? So imagine if, yeah, the circumcenter is going to be right here. That's not where I want it. The circumcenter is equidistant from the vertices. I want something that's equidistant from the streets. So I'd be looking for the in-center, right? The in-center, which is actually really hard to do, right? So I would be looking for the in-center here. In-center would be my answer. Because it is equidistant. Equidistant. Here we go. From the 3 sides of the triangle. All right. Well, cool. So thanks for watching, internet friends. Hope you have a great day. Bye-bye.